Hi guys, in this video I will discuss degrees of unsaturation, DUS. Now DUS is a very important concept, very useful for you if you will take the time to understand it. Now DUS is sometimes called hydrogen deficiency index, but very rarely. Most of the time it's going to be referred to as degrees of unsaturation, DUS. DUS can be determined two different ways, either from structure or from formula. Let's first look at doing it from structure. First off, we need to know that one double bond equals 1 degree of unsaturation, 1 DUS. While one triple bond, and that's my T there, is equal to 2 DUS. Now actually what's going on here is each pi bond is 1 DUS. But since a triple bond contains 2 pi bonds, that's why a triple bond is 2 DUS. Now once we start covering bonding more in depth and looking at hybridization and sigma bonds versus pi bonds, etc., we'll see that a triple bond contains the 2 pi bonds and thus 2 DUS. Now we also need to know that one ring equals 1 DUS. Now we'll explain this further as we move along. As an example, hydrogen cyanide, HCN, Lewis structure here. We see a triple bond between the carbon and nitrogen. It's a cyano group. Triple bond is 2 DUS. We don't see any other double bonds or triple bonds or rings in this molecule, and so the answer is 2 DUS. Now ultimately that means it's missing 4 hydrogens compared to max. Well, what do I mean by max? I mean compared to this structure, which has the same 1 carbon and 1 nitrogen. If we got rid of the triple bond and completed all valencies using hydrogen instead, we would put 3 H's around carbon, 2 H's on nitrogen, lone pair on nitrogen, standard bonding for carbon and nitrogen and hydrogen, and we can see that the C and N can actually hold 5 hydrogens total. Where up here in this structure it only had 1. And so we can say it's missing 4 compared to max. This is max. We call that saturated with hydrogens, or the maximum number of hydrogens for the given number of heavy atoms. Since this is saturated, well, that's why it's considered to be no degrees of unsaturation. It has no unsaturation. 0 unsaturation. It's saturated. Of course, we can tell that by looking at structure. How many double bonds do you see? None. Triple bonds? None. Rings? None. That tells us there's no degrees of unsaturation. But up here we see that this compound has 2 degrees of unsaturation. And one thing we need to know is for every DUS, we can say 2 H's missing. With each DUS, 2 H's missing. Now this is probably going to be stated down below. 2 DUS means there's 4 H's missing compared to max. Okay, let's do some other examples. This simple alkene has 1 double bond, and 1 double bond would be 1 DUS. There's no triple bonds and there's no rings. Since there's one DUS, how many H's are missing from max? Well, for every DUS, 2 H's are missing. There's 2 missing. We can see that by looking at this compound. If instead of having a double bond between the carbons, we completed the valencies of carbon with just H's all around, we would have 3 H's on this carbon and 3 H's there, and that would be a total of 6 H's, but this is only 4. It's missing 2. Well, we knew that because every DUS means it's missing 2 H's. Now let's try an example with a ring. Let's take this 3-membered hydrocarbon ring, all carbons. The smallest ring you could have is 3 carbons. It's not possible to have a 2-carbon ring. The formula here is C3H246H6. Let's work with structure though. Any double bonds? No. Any triple bonds? No. Any rings? Yes, 1 ring. And so 1 ring indicates that this has 1 DUS. Now, for 3 carbons, if we open the ring and filled all valencies of carbons with H's, you would see that we would be able to get 8 H's around the carbons and have a compound of C3H8. And so for 3 carbons, 8 H's is the max. But this compound has 2 H's less than max. And 2 H's less than max indicates there's 1 DUS. Well, now I'm working with formula. We'll repeat that below. But we can see that it has 1 DUS by looking at structure if we know this right here. Now see up here, to put in a double bond here, you got to remove 2 H's. Then you can double bond these and get that structure. Now down here, we're not putting in a double bond, but we're making a ring. And to make a ring, you got to connect the 2 N carbons here. And for them to connect to bond, you first have to remove 2 H's. Thus, a ring has 2 H's removed compared to the open version. And when you remove 2 H's, that's ultimately a DUS. Okay, how many DUS does ibuprofen have? Now we got hole punched here. This is just plain alkane group, an alkyl group. Carbon, carbon, boom, boom. Basically there's no double bond here. There we go. I kind of got it drawn in there. Carbon, 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 carbon. No double bond. There's no DUS here. But how many DUS do we see over here? I see 1, 2, 3, 4 double bonds and 1 ring. So that is 5 DUS. Now, sometimes my benzene rings, the pi bonds, I'll draw them in kind of quickly. Officially, it's boom, boom, boom. But sometimes I may draw them sort of more quickly, boom, 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 and they may not quite line up. Now, some chemists will actually just draw a circle. For other reasons, I would recommend never doing that. But just to let you know that my pi bonds may not precisely line up, boom, boom, and boom. Okay? Four pi bonds plus a ring, that adds up to 5 DUS. Okay, let's move to formula. Both discussions sort of include structure and formula, but let's focus on formula now. And first, hydrocarbons only. compounds that only contain C and H. It's important to know that your maximum number of H's, that is a compound that's fully saturated, and we can tell from structure that that's fully saturated. But if you want to do it from formula, you first need to know that maximum number of H's is calculated by the 2n plus 2 formula, where n is the number of carbons. As an example, if we had a compound with 5 carbons, we would need, put 5 in here, 2 times 5 is 10, plus 2 is 12. You would need 12 H's for the compound to be saturated. Thus, this formula tells you that C5H12 is a saturated compound. Now that's very powerful. If you know this is the formula, you know that this compound cannot have a double bond or a triple bond or a ring, because this compound has 0 DUS. It's fully saturated. It has no unsaturation. So the formula now tells you a good bit of useful information about possible structure. Now, on the other hand, what if you had a formula C5H10? Well, compared to max, first off, you need to know what max is for 5 carbons. For 5 carbons, 12 is max. If you've only got 10, you know you're short 2. Okay? 2 H's less than max. 2 H's less than max, we said, is 1 DUS. Okay? We're just kind of saying it a different way. So we know from formula that any compound with this formula is going to have 1 DUS. That's very powerful again. Thus, any structure with this formula must have either 1 double bond or 1 ring, because either one of these is 1 DUS. But we also know that the compound with this formula cannot contain a triple bond, because a triple bond would be 2 DUS, and this formula does not indicate 2 DUS. It indicates only 1 DUS. We could do another example here. What if we had, let's do different number of carbons. What if we had C7H10? How many DUS would be present in a compound with this formula? Well, C7, what is max? 2 times 7 plus 2 equals 16. All right. How many are we missing? Missing 6 H's. How many DUS is that? Well, for every 2 you're missing, for every 2 H's you're missing, that's 1 DUS. So really, we just divide this by 2, right? That's 3 DUS. All right, missing 6 H's. For every 2 H's you're missing, that's 1 DUS. For every 2 H's you're missing, that's 1 DUS. Up here we said for every DUS, that's 2 H's missing. We just said it in reverse. 3 DUS. So we know something about this potential compound. The compound would have how many triple bonds? This compound could only have 1 triple bond. Can't have 2. If it had 2 triple bonds, that equals 4 DUS. Right? The compound only has 3. one triple bond. So we could have one triple bond plus one double bond. Or it could have three double bonds. Or it could have three rings. Or it could have two rings and one double bond. Basically, all this equals, any of these equals 3 DUS. All right? Very powerful. So if you're asked to draw a structure, knowing your options, again, very powerful, very useful. What about when heavy atoms are present, or heteroatoms? Well, same as above. We still want to use our 2n plus 2 formula. However, we have to know how to count these heavy atoms. And that is stated right here. When you have a halogen, it counts as a H, or hydrogen. A nitrogen subtracts a hydrogen. We're going to have to explain these two. Oxygen is simple. Just ignore it. Okay? For example, over here, if I had a formula of C7H10O, I would just ignore the oxygen. Just ignore it. It's the same as C7H10 in this calculation, and that's also 3 DUS. All right? Just act like it's not there when you're doing your DUS calculation. But what about halogen? Okay. Well, let's do C7H9Br. How does halogen count? It counts as an H. So if you're working with this, we can effectively count that as an H and change this to C7H10. And now that we're treating it like that, we see it has 3 DUS, same as below. Now, when I drew this, I had to reduce that to 9. You're not going to have a formula C7H10Br. That's actually not possible. Because ultimately, when you bring in the bromine, it has to replace an H. We're just going the other way. We knew it replaced an H, so if we want to just show all hydrogens, we can add that H back and treat the formula like this. Now we can easily get and see that that's 3 DUS, just like we did down here. What about nitrogen? If we do nitrogen, well, I know I'm going to have to call this H11N. And how do we treat nitrogen? Nitrogen, you subtract an H. So this subtracts an H, and this becomes, guess what? H10. And now we're back to easily 3 DUS, just like we saw down here. The reason that is because if you have a compound, well, like this, you can just replace an H with a halogen, because the halogen makes one bond just like H. But you can't just replace the H with a nitrogen. If you put a nitrogen there, you have to add things here. And actually, if you add H's, you have to add 2 there. And you actually end up with 1 more than you had here. You've got 1 more than you should because of the nitrogen. That's why we subtracted 1. In the end, if you remember it here, Now we can do a larger example. Prozac, the structure is shown on the drug sheet, practice sheet on like page 2 or 3. And we'll look at that. We'll look at the structure, but first let's determine DUS from formula. Then we'll look at page 2 in the workbook. From formula, here's the formula. How do we treat halogen? We've got H18. Halogen counts as H. So we can change this to H21. Nitrogen, we subtract an H. So this goes back to H20. And what do we do with oxygen? Just ignore it. That's a 20, not an oxygen. So we have effectively C17H20 after we accounted for the 3 halogens and the nitrogen. Now we can do DUS. Sorry, that was a little low. We started with 18, we added 3 to replace the 3 halogens, but then we subtracted 1 because we had a nitrogen. It got us to this hydrocarbon formula, which we can now work with. C17, 2 times 17 plus 2 equals 36. So we only have 20 H's, we're missing 16 H's. So how many DUS is that? Well, every 2 you're missing is a DUS. So effectively you divide this by 2 and we have 8 DUS. We just determined it from formula. Prozac has 8 DUS. Now we can look at structure. And the structure is here. And hopefully you see the 8 DUS. That is 6 double bonds and 2 rings. 6 plus 2 is 8 for structure of Prozac. Now, of course, there are numerous different structures you could draw that have this formula, many different constitutional isomers, but they would all have 8 DUS. They have to. If they did not have 8 DUS, then something is wrong. You either have incorrect bonding, or you have the wrong number of H's, or something is wrong with your structure. Okay, so that's DUS. Very powerful, as hopefully I have showed. You can determine it from either structure or formula. Now, there is another formula out there where if you forget these things, how do you count a halogen? And by the way, sometimes you can get confused here. I've seen students go the wrong way. It's hard to explain that, but sometimes I've seen students start adding an H when actually they subtract it. There's a formula out there, 6n plus 2 minus a divided by 2, to give you the DUS. Here you treat every atom the same, and n equals